Hi everyone. So today I have for you a British Maths Olympiad 2001 problem, which is actually a geometry problem. Okay, and the problem is actually really nice. So let me draw out the problem for you. Okay, so where is my white chalk? Here it is. Okay, so Let me draw out the problem for you. All right. So the problem goes like this. You have a triangle ABC. Okay, something like this. Okay. Now, clearly, this angle seems smaller than this angle, and it's been given in the problem that angle C is bigger than angle B. So let's call this angle C and this as angle B. Okay. And let's call this as angle A. All right. Now, the next thing that is given in the problem is that the internal angle bisector of ABC meets the opposite side at D. That is, so let's try to draw an internal angle bisector. Okay. It meets at D. Now you have these two angles equal. So let's mark equal angles by same color. Okay, so let's mark equal angles by yellow color here. So both are a by 2 essentially. Okay, both are a by 2. Let's remember that. All right. Now the next thing they've given in the problem is that point E is on AB. Okay, point E is on AB such that okay, I think I should interchange C and B. So it's given that, so let me interchange C and B. It's been told that angle C is bigger than angle B. And I think this angle is actually bigger. So let's make it C and B. Okay. Then, now it's been given that the point E is on AB. Now it can be on AB. The point E is on AB such that EDB is 90. What does that mean? If you erect a perpendicular at D, let it go and meet AB at E. Okay, so that's what it means. So let's just erect a perpendicular at D, okay, and it will meet AB at E. So now EDB is indeed 90. Okay, this is 90. All right. Next, what you have to do is locate a point F on AC such that BED is DEF, meaning you want to sort of reflect BE about ED so that it falls onto that line cuts AC at F. Let's put it. So let's draw it. So if you try to draw essentially something like this, okay. So this is it. And again, notice it's given in such a way that this angle here, the pink angle, and this pink angle are equal. It's constructed in that manner. Okay, you're constructing F such that FED is equal to DED. All right. So now you are asked to prove the following. You're asked to prove that FDC. So let's join F to D. Okay. You're asked to prove FDC is equal to DAB. Okay, or whatever BAD. So prove. Let me write it here. So you need to prove that angle FDC is equal to angle BAD. But remember, BAD is just A by 2. Okay, because this is overall angle A. So in other words, you have to prove this is a yellow angle. Okay, this angle and this angle are equal, or this angle and this angle are equal. It's basically A by 2. How do we prove that? All right. So I want you to pause and just think about this for a minute. The hint is here. If you want a real hint here, I can give it to you. But if you don't want a hint, pause it right now and try the problem. Okay. If you want a hint, if you tried for a while now and you want a hint, then notice that there are two angle bisectors in a problem. Two angle bisectors. Do you know configurations where there are two angle bisectors? Okay, all right. Now let's come to the solution. Solution is really easy. Notice that there are two angle bisectors in a problem. And what does this mean? It means that, and we know that whenever two angle bisectors meet, you have some in-center or x-center. And in this case, indeed, you can see that these two angle bisectors are essentially if you look at it carefully, you'll see that it is the internal angle bisector here and an exterior angle bisector here. So put in other words, if you look at triangle AFE, if you look at this particular triangle, okay, the blue color shaded triangle, I guess, okay, if you look at AFE, then for that triangle, you see that this AD line is the internal angle bisector as given in the problem, and this ED line is essentially the exterior angle bisector because FEB is an exterior angle at E for triangle AFE. This is an exterior angle. So this is an exterior angle bisector, and the exterior angle bisector and the interior angle bisector are concurrent at the x center. So D is the AX center of AFE. So I'm going to write a bunch of facts now, okay, for the proof. Okay, so let me notice that ED is the exterior angle bisector is a exterior angle bisector, because there are multiple exterior angles. Exterior angle bisector of a triangle AEF. Okay, this immediately implies that D is AX center, because meeting point of angle bisector is AX center of essentially triangle AFE. What does that mean? It means that FD is also, remember here, EFC is also exterior angle, right? EFC is also an exterior angle. And since the three angle bisectors are concurrent, FD must be an exterior angle bisector. So FD is an exterior angle bisector, for triangle AF. Okay, AEF or AFE. Sometimes I say AEF, sometimes I say AFE. Now that tells us something interesting. It tells us that these two angles are equal. Okay, and now we just have to chase angles. So let's start chasing the angles. First, we note that since this is 90 and this is angle B, these pink angles are 90 minus B. Okay, so let's write those angles in the diagram. This is 90 minus B, and this also is 90 minus B by construction. In fact, we have constructed so that these two angles are equal. All right. So if this entire angle is totally 180 minus 2B by, angle sum, I mean, if you look at the linear, these three things are, add up to 180. So they are on a straight line. So AEF is easy to calculate. Okay. So we can calculate, first of all, what is AEF? AEF is 180 minus angle FEB, which is 180 minus 2B, which means it is just 2B. Okay, so angle AEF is 2B, this angle is 2B, and this angle is A. So we therefore can easily calculate what is this exterior angle. The exterior angle EFC is the sum of interior opposite angles. If you take EFC, it is the sum of these two interior opposite angles, which is angle A here, okay, plus angle, so if you want, let me write one more step. So it is nothing but the interior opposite angles FAE plus FEA. Okay, and FAE is angle A, and FEA we just now proved is 2B. So therefore, we know EFC is actually nothing but A plus 2B, but we know FD is an exterior angle bisector. So it cuts that total angle into half, right? So which means that we therefore get angle CFD to be angle EFC by 2. Okay, you get EFC by 2, which is essentially A plus 2B by 2, which is A by 2 plus B. Okay, now using this all pieces of data, we get basically this angle. Okay, all right, so now that we have shown CFD is A by 2 plus B, all that remains is to chase angles and get angle FDC. We have to show it is actually the yellow angle, so we have to show it's A by 2. Let's see, let's finish off the angle chase. All you have to do is angle sum property here. So angle sum property tells us that angle FDC is 180 degrees minus angle FCD, which is angle C, and minus angle CFD, which we know is A by 2 plus B. Okay, and we know, of course, that 180 is A plus B plus C. That's the sum of angle sum property on the full triangle ABC. Minus C minus A by 2 minus B. Minus P minus C minus C cuts, and minus P plus B cuts. What remains is A minus A by 2, which is A. This is what we had to show. We had to show FDC is A by 2. So we're done. Bye.